So before I talk about these S arithmetic groups and what a small subgroup is, I want to add one addendum to yesterday's talk. That let's put this over here, I guess. When Matt was talking about how to try to prove that PSL2Z doesn't have the congruent subgroup property, I think what he meant to talk about was when you have a surjection onto A6, that proves it can't, the kernel of that doesn't have the congruent subgroup property. A5 is not big enough because A5 is actually a congruence quotient. It's the quotient of PSL2Z by the matrices that are congruent to 1 mod 5. So A5 isn't big enough, but A6 is big enough. So that's relevant to the project people are working on about these other S arithmetic groups maybe not being congruents. We have to start using surjections onto A6. A5 isn't big enough. Okay, so let me come back now to the main theme. Okay, I want to talk about S arithmetic groups and what's a small subgroup of such a thing. So last hour, the arithmetic groups were coming from central division algebras over some number field. And the kind of things we were doing was to take an order inside such an algebra and look at its unit group or its S unit group. Okay? Now, one way to think about subgroups of such things is to say, well, these kinds of division algebras over number fields can have many, many subdivision algebras defined over smaller number fields. And I'll talk about very explicit examples of how that happens. So one way to say that some elements would be small is to say that they come from units in subdivision algebras over smaller number fields. Okay? That's a different sense of smallness than height. So the idea I want to talk about today is to say, if I take an arithmetic subgroup, and I'm going to remind you what kind of groups I'm talking about, inside the multiplicative group of the division algebra B, the issue is we can look at the intersection of that group with the unit groups of subdivision algebras and look at all the subdivision algebras that aren't as big as B. Then I get a collection of subgroups, and the issue is, are those subgroups big enough to generate something of finite index in the original gamma? If that's true, then you can generate by small subgroups the elements of these arithmetic groups. Our original idea was, to try to simplify the problem when we had a division algebra over, say, a real quadratic field, try to simplify it to finding the units in these arithmetic groups for division algebras over Q. Maybe lots of such division algebras over Q, but it tends to be easier when you're working on something that's smaller division algebra. And so the first part of the talk will be about this from a purely algebraic standpoint. And then toward the end, I'm going to talk about how this question is naturally connected with looking at Shimura subvarieties of Shimura bricks. And in particular, Shimura curves sitting on Shimura surfaces. And how much can you generate the fundamental groups of Shimura surfaces by fundamental groups of Shimura curves that are sitting on that surface. So the geometry is pretty. A little bit too big, but okay. So let me talk about the algebra per se before doing some geometry. So I want to focus on a very concrete case, which was really what motivated a lot of what we've done. Suppose we take this F to be Q and K as a real quadratic field. I'm going to think of those as fixed. And I take a quaternion algebra that's a division algebra over K. So it's a dimension 4 over K. And if I tensor with the algebraic closure of K, I get 2 by 2 matrices over the algebra. Now, one question is, if you take such a division algebra over a real quadratic field, when does it come from a division algebra over Q? When is it a base change of something over Q? And there's a very simple answer to this. that comes from the theory of the Brouwer group. It says that if you look at your quaternion algebra of the real quadratic field, it comes from something over Q precisely if two things occur. If you have a place of the real quadratic field that's not split over Q, then locally, when you take completions, the division algebra has to be a matrix algebra. It has to be the trivial algebra locally. And if you take two places that are split over the same place of Q, well, then the completion of K at W and W prime is both isomorphic to the completion of Q at a certain place. And it makes sense to say these algebras have to be isomorphic. They're either the matrix algebra or, up to isomorphism, the unique division algebra that's a quaternion division algebra over the corresponding completion. But they have to agree at two places that lie over the same place of Q. Those conditions are pretty natural. And there's lots of ways to construct this. Like you can start with a division algebra over Q and just tensor it up to K and insist that at some place it remain a division algebra. And once you have this result, it's pretty easy to see that once you have one division algebra over Q that gives rise to your thing over K, there's infinitely many. And I'll explain that. Basically, the idea, and it's on the next page, the idea is that these division algebras have classes in the Brouwer group, and they're determined by their classes in the local Brouwer groups. And once you have one B sub Q that gives you B, you can make another one by simply changing the local invariant of the algebra over Q at any place that does not split. Then the effect of that disappears when you take the tensor product. So let me just do a little Brouwer group theory to explain why this is true. It's connected nicely with what Julia and David have been doing. So the idea here is that we look at the original algebra B in the Brouwer group of K, and we're trying to see if it comes from the Brouwer group of Q. So there is a natural map from the Brouwer group of Q to the Brouwer group of K. It's just a tensor product map on algebras. Elements of the Brouwer group are determined by their local, division algebras they give rise to on completions. And there's this standard description of the Brouwer group of Q and of K. Namely, we know what the local invariants look like. They're either in Q mod Z or 1/2 Z mod Z. For division algebra, all the local invariants are of order 1 or 2. The local invariants are either 0 or 1/2. And the global Brouwer group is described by everything where the sum of the local invariants is 0. And the map on the local Brouwer group level is just multiplication by the local degree. So if you want to get something in the Brouwer group of K that's in the image of the Brouwer group of Q, you just trace through this little diagram, and you see that the condition is that the local invariant of the element of the Brouwer group of K has to die at those W that have relative degree 2 over the corresponding place of Q. And otherwise, you have to have, when you take places that split, you have to have the same invariant at the two places above a given place of Q. So that's a little bit of algebra. But it also explains why you can find infinitely many quaternion algebras over Q that give rise to B if there's one, because I'm free to change the local invariance of the algebra over Q at any place B that doesn't split, because then the effect of making that change disappears when I pass the tensor product over K. So that's the algebra story. So let me come back to this question of trying to generate arithmetic groups by small subgroups. So here's the problem that we're thinking about. Is there something? Yeah, okay. Oh, good. Okay. All right. So the scenario is this, that I have this quaternion division algebra B over the real quadratic field K. And last hour I talked about how you construct arithmetic groups from such a thing. You need to take an order in there for the ring of integers. It's just a finitely generated module for the ring of integers, which spans it as a vector space over K. And to construct an arithmetic group when S is just the set of Archimedean places, you look at the reduced norm from B to K, and you restrict that to, say, the unit group of this order. Now, I should emphasize what the reduced norm means. If you take your quaternion algebra B over K, when you tensor with the algebraic closure of K, you get a matrix algebra. And you can just take the determinant function on that matrix algebra. That turns out to map B to K when you take determinants. So the reduced norm is this multiplicative function. And I want to look at the kernel of the reduced norm map. If this algebra had been the 2 by 2 matrices, for example, over K, the order we could have taken would be SL2 over the ring of integers. Okay? I'm sorry, the order would have been the 2 by 2 matrices over the ring of integers. And this D sub 1 thing would be just SL2 over the ring of integers. Now that's what would happen if B was a matrix algebra, but I don't want to take the matrix algebra. I want to take division algebras. But you should think of D sub 1 as the non-commutative version of SL2 of the ring of integers. And the issue is, in the case in which B comes from infinitely many different quaternion algebras over Q, can we generate this arithmetic group D sub 1 by its intersection with those quaternion subalgebras over Q? I'm going to let the quaternion algebra over Q range over all of the subdivision algebras over Q, which tensored up with K give you B via sum embedding. This is kind of analogous to asking whether, if you look at all ways of embedding the 2 by 2 matrices over Q into the 2 by 2 matrices over K, can you generate all of SL2 of the ring of integers of K by the images of SL2 of Z? Okay. You would generate something and find an index under that. But in our case, we don't want to take the split algebra. We want to take division algebras. So let me just finish this slide by saying that what's really happening here then is that we got an arithmetic group defined by division algebra over K. There's infinitely many subgroups defined by all of these quaternion algebras over Q inside B. And each of them gives rise to its own little arithmetic subgroup. And we want to know, are those big? Do those generate something big or not? So if I take one of the quaternion subalgebras and intersect it with a big order, I get a Z order in the quaternion algebra over Q. And our original thought was that finding the units in those things should be easier. And if you can do that for enough things, maybe you can generate the big group in an easier way. Well, so that was all the algebra. Now, let me say a little bit about geometry. The geometry of the situation is quite nice. So here's the geometry. So we're starting with this division algebra over the real quadratic field, which comes from a division algebra over Q. It can do that in many, many ways. Okay? But the B is fixed, but the B sub Q is not. Now, if you take the real place of Q, it's going to split into two real places in the real quadratic. And one of the things we talked about last time was how you need to look at these division algebras and look at their Archimedean parts. Namely, you tensor them over Q with the roots. Now, if I do that for the quaternion algebra over Q, there's only one infinite place. So when you tensor the quaternion algebra over Q with R, you get the 2 by 2 matrices. And that upper 1 there means you take elements of reduced norm 1, so you just get SL2R. So you get a copy of SL2R coming from the quaternion algebra over Q. When you do the analogous thing for the quaternion algebra over K, when you tensor that with R over Q, you get the direct sum of two matrix algebras over the reals. And when you take the elements in reduced norm 1 in there, you get product of two copies of SL2R. Now, the fact is that there is a natural map from the quaternion algebra over Q into B. And that ends up giving you some map from your one copy of SL2R into the product of two copies. And you can be explicit about how to do that once you choose these local isomorphisms of Archimedean completions with a 2x2 matrices. Okay, so now here's where the geometry comes about. If you, one way to think about the upper half plane, which I've tried to sketch a little bit down here, is that it has a natural action of SL2 on the upper half plane, right? The upper half plane is x plus I y, so the y's are positive. And elements in SL2 act on the upper half line by fractional linear transformations. Now, if you take the point I in the upper half plane, then the stabilizer of I is SO2R. So the map from SL2R down to the upper half plane is you just take right cosets of SO2. So I don't want to complicate my slide too much, but you just take a matrix here, and you let it act on I. If this matrix is a gamma, say, I let it act on I by fractional linear transformations. And that's the same thing as looking at the coset of your original matrix with respect to the stabilizer of I, which is SL2. Okay, now we have a map from SL2R into the product of two copies of SL2R. It comes from the embedding of the quaternion algebra over Q into the 1 over K. And that map then maps this point in the upper half plane to a point in the product of two upper half planes. So we should say what the product there means. You need to take SL2R across SL2R and divide out by some compact subgroup. And the compact subgroup that I want to take is the SO2R on the left, push it forward, and then look at each of its projections and take the product of the projections. And that will end up giving you upper half plane cross upper half plane. So associated to this embedding of B sub Q into B, there's a map from the upper half plane into the product of two copies. And the metric on the upper half space is the usual one. If you look at z equals x plus iy, you just write down this line element. That's how you measure distance. You integrate that over arcs. The geodesics in the upper half plane are either vertical lines or they're pieces of circles that intersect the boundary at right angles. And on upper half plane cross upper half plane, you have the product metric. And this embedding of the upper half plane into the product is a totally geodesic embedding. It's a nice embedding. So good. So the algebra gives you a way of putting inside upper half plane cross upper half plane lots of geodesic copies of one copy of that upper half. Now the question is, how does this relate to the arithmetic groups? So let's try to keep this all straight here. I wanted to study the arithmetic group D upper 1. So that's the units of norm 1 in an order in the big quaternion algebra D. Okay? So I take that D sub 1, which is a nice finely generated arithmetic group. It may have torsion, so I don't really want to deal with torsion when I'm constructing varieties. I don't want orbifolds, I want real manifolds. So I'm going to take a subgroup of finite index in D sub 1 that's torsion-free. Not so hard to prove that exists. Now, given that subgroup, the torsion-free subgroup of finite index, whenever I take one of these quaternion algebras over Q with the property that they give rise to B, then I can form an arithmetic subgroup of the order in the quaternion algebra over Q that you get by intersecting the big order with that quaternion subalgebra. Each of the quaternion algebras over Q give rise to, and the choice of D up there gives me an order inside a quaternion algebra over Q, and I can look at the units of norm 1 in that live in my subgroup gamma. And that is the subgroup of gamma that comes from that particular quaternion algebra. Now the geometry then looks like this when I take the subgroup that's associated to a fixed choice of quaternion subalgebra, taking that subgroup, it acts in a discrete way on the upper half plane. And because these are division algebras, sorry? Okay. All right. Technical troubles. The subgroup gamma prime, which is a subgroup of units of norm 1 in an order in a quaternion algebra over Q, is acting on the upper half plane in a discrete way. And because it's a division algebra, the quotient is a compact Shimura curve. For example, if you can construct a fundamental domain for that thing in the upper half plane, that's a nice compact set bounded by finitely many pieces of geodesic arcs. And actually, one of the things that comes out of this Lenstra business is an algorithm for producing those fundamental domains. You can get a picture of that. But on the other side, when I take the product of two upper half planes and divide out by my big arithmetic group, then I get a compact Shimura surface. So these things solve various moduli problems. On the left side, it's abelian surfaces with quaternionic multiplication, and on the right side, it's something else. But there's a lot of theory about how to construct models for these varieties over number fields. Okay. So the algebra situation where you have a quaternion algebra over K that comes from lots of quaternion algebras over Q produces this compact Shimura surface on the right with many, many different Fuchsian curves inside it. One thing one should watch out for here is that when you look at the Shimura curve on the left, it will be a smooth curve, okay? Smooth projective curve defined over number field, because I insisted the gamma prime has no torsion. But when you map it forward into the surface, it could start crossing itself. You could get some extra crossing points, basically because there's ways to identify cosets. Well, if you think about it in terms of orbits, there's extra elements of gamma that might be producing additional identifications of points in addition to the ones produced by gamma prime. But there'll be finally many crossing points, right? Because everything's compact. So you have a nice smooth curve getting mapped into a surface in a way that might involve some extra crossing points. So what we're trying to figure out from the geometric standpoint, the geometric version of the algebra that I'm talking about is how much can you say about the compact Shimura surface by studying the curves on it that are Fuchsian and arithmetic in this sense. And what kind of thing would you want to try to determine, for example? Well, here's the most basic question about the connection between these curves and the surface. So we've got infinitely many Fuchsian curves coming from the fact that there were infinitely many quaternion algebras over Q that gave the same algebra over K. And one problem that we thought a lot about is whether the fundamental group of the surface is generated up to finite index by the fundamental groups of these curves. And that's really just a geometric reformulation of the question of whether the units of norm 1 in the big order over inside K are generated up to finite index by the units of norm 1 in the intersections of that order with the quaternionic subalgebras over Q. So this is the geometric version of that question. And we thought a lot about this. We can't prove this yet, but we could prove something that's a little weaker, but nonetheless gives you some nice consequence that I'm going to talk about. And Matt will go into the technique that's involved here, but it's a kind of an important thing to have heard about. The so-called Lefschetz theorems are all about taking a big algebraic variety and looking at subvarieties. And if the subvarieties are sufficiently positive in some particular sense, the fundamental groups of the subvarieties will generate a subgroup of finite index in the big one. So that kind of application is known as a Lefschetz theorem. And Matt will be explaining what the technology is behind that. And clearly that's what the kind of result we want to apply here to get the fundamental group of X generated by small subarrays. Well, let me talk about a version of this question of getting the geometry of X from geometry of curves on X that has to do with a thing called the Albanese variety. So this is a kind of a geometric version of the question of generating fundamental groups. You can think of it as, yeah, exactly that. It's like an abelianized geometric version of this question. The Albanese variety is something that I think people have actually been working with for a long time in the form of Jacobians. It's a generalization of the Jacobian of variety. So if we take any variety X, the Albanese variety is an abelian variety that's universal with respect to maps from X to abelian varieties. So that it's an abelian variety that you can, I'll go through the construction in a minute. It's an abelian variety to which X has a morphism, and so that every morphism from X to an abelian variety factors uniquely through the Albanese. So here's a way to construct it. I should say to begin with that if X were a curve, the Albanese is just a Jacobian. That's obviously what you would think. So it's a generalization of the Jacobian. And a way to do it, it's very concrete, in fact, is you take the global holomorphic forms, global holomorphic 1 forms on your X. And imagine that omega 1 through omega n are a basis for those things. And then you fix a base point, S sub 0, on X. And you just map a point little s on X to the vector you get by integrating those forms along some path from the base point to S. Well, that will give you a vector of complex numbers, which actually defines a homomorphism from the holomorphic 1 forms to C. But of course, it depends on path. So when you divide out by the ambiguity caused by the path, you divide out by a period lattice. So this is nothing other than the construction of the Jacobian, the map to the Jacobian on a curve. It's exactly the same thing. You take a basis for the space of holomorphic differentials on a curve. You do this. Okay, so one sort of functorial, one consequence of the universal property of the Albanese is that if I take my surface X and look at the map to its Albanese, I have produced lots of these curves, C sharp, which are living on X. Okay. Well, if I map C sharp to X and then forward to the Albanese, that's the map from C sharp to the Albanese. Well, now the Jacobian is the Albanese. The Jacobian of C sharp is the Albanese of C sharp. So by definition of the Albanese, or the functorial property, there has to be a unique morphism from the Jacobian of C sharp to the Albanese of the surface. So we were originally interested in whether you could generate the fundamental group of X by the fundamental group of these embedded Fuchsian curves. Okay, we don't know. But you can ask whether the Albanese is generated by the images of the Jacobians. That's kind of the abelianized geometric version of the question. And that, at least, we can show happens. So I'm going to be ending kind of early today. But this is the theorem that we want to go for next time. That you can find finally many Fuchsian curves that come from quaternion division algebras over Q that base change to your B, as long as the B comes from at least one such thing, so that the Jacobians of those things generate the Albanese. The morphism from the product of the Jacobians to the Albanese is surjective. So I think maybe, let me just make one other comment here. So far, since I have a little more time to say something, then I'll stop. We've been talking about quotients of the product of two copies of the upper half plane by these discrete subgroups, and we've been looking at curves on them which come from sub-quaternion division algebras. Now, this just arises from taking quaternion algebras over real quadratic fields and generating by subalgebras. Now, instead of taking quaternion algebras, you could take algebras that have dimension 3 and some additional structure, and then look at generating them by subalgebras. And so maybe next time Matt will say a little bit about, I don't want to force him to do this, but there's something called the complex hyperbolic plane that arises from division algebras of dimension 9 over their center. And you can similarly look at these kinds of, this kind of problem for those groups, where you get other surfaces and other natural curves. And all of this has some counterpart in that world where you're taking somewhat different division algebras. So that the overall theme of this would be to say, when you take arbitrary division algebras and you look at the ones that come from division subalgebras, how much can you say about the geometry of arithmetic quotients associated with the big ones from arithmetic quotients of the small ones by using Lefschetz theorems to try to control the situation. So I think I'm actually going to stop early and give people a break. Oh, well, back in the algebraic world, that's a good question. Back in the algebraic problem, let me see if I can get it up here. If you don't take reduced norm 1, then the reduced norm will map the big order to the unit group of the real quadratic field, for example. And it will map the unit group of one of these quaternion orders over Q to the unit group of Z. Well, the unit group of Z is just plus or minus 1. And the unit group of the real quadratic field is infinite cyclic. So there's an obstruction. There's an obstruction when you don't take reduced norm 1. Because the image of the norm will in general be a finitely generated subgroup of the unit group of the real quadratic field, which would be infinite. So you couldn't possibly generate everything in the unit group of D from these quaternion subalgebras over Q, simply because the reduced norm of anything that comes from such a subalgebra is either plus or minus 1. So there is that's why you need to deal with units of reduced norm 1. Well, there is, since you asked, if you don't mind, there is one fact that I'll mention. You can ask this without passing to orders. There is one interesting fact here. So if you look at you can just ask the question, what about generating the units in the whole division algebra by elements in B sub Q stars. Okay. Again, you're going to have a problem with reduced norms, because the reduced norms of something in a subalgebra is going to be in Q star. Units in B star will be if something's in K star, and you're going to have this gap. But there is this fact that every element gamma, which is a unit of reduced norm 1 in the big algebra, can be written as a product where each of these guys, well, they live in a subalgebra that's a quaternion division algebra over Q, but all we know is that they're actually just invertible. We don't know that you can force them to be of reduced norm 1. So at least as far as the units of norm 1 in the big algebra go, if you forget about integrality, you can generate them by things that come from quadratic subalgebras. But again, we can't force it to have reduced norm 1. The question of making these gamma i's have reduced norm 1 leads to some interesting problems about finding integral solutions of homogeneous quadratic forms over Z when you know there's integral solutions over every completion of Z. which is also related to what David and Julia talk about. So I've been pestering David about this for some months now. How to get these patching theorems to work over Z. If you had patching theorems over Z, it would be very relevant to this question of generating arithmetic groups by subgroups. Because finding points in these arithmetic groups is sometimes equivalent to solving homogeneous forms over Z. You want the reduced norm to be 1. Reduced norm is in general a homogeneous quadratic form. So that's I guess, an ad for Julia and David's work. It has another application. If we could just do it over patching over Z, which I think is something that David's been thinking about for some decades.